Welcome back to the deep dive. Today we're doing something a little different. Usually we look at the actors on the stage, the proteins, the DNA, the enzymes, all the stuff of life.
Right, the main characters.
Exactly. But today we're looking at the stage itself. We're looking at the medium, the context. We are talking about water.
You know, it's the most abundant substance in living systems, but I think, and I say this with a lot of love for the field, it is probably the most misunderstood and glossed over chapter in the textbook.
I think that's so true. For most of us, water is just background. It's the packing peanuts of biology. It's the filler that cells float in so they don't, bump into each other.
Yeah, passive solvent.
But we've got a stack of research here today that completely flips that narrative. Specifically, we're synthesizing two absolute titans of the field: Leninger's Principles of Biochemistry and Harper's Illustrated Biochemistry.
These are the Bibles of the subject.
Okay.
And the reason we're pairing them is very intentional. If you look at the chapter, Water, the Solvent of Life in Leninger, you get this incredible, deep, systems-level physics view.
It tells you why the universe behaves this way.
Exactly.
Yeah.
And then Harper comes in with its Water and pH chapter and basically says, okay, and here's how that physics can kill you if it goes wrong in a hospital.
Right. Harper gives you the clinical reality, the fluid dynamics, the pH balance, the stuff that keeps a patient alive in the ICU.
That's it. So our mission, really, for this deep dive is to synthesize those two perspectives.
Yeah, we want to stop looking at water as this passive background and start seeing it as an aggressive, active participant in molecular architecture.
It's the invisible architect.
I love that. The invisible architect. So, disclaimer right up front. This is not a substitute for reading the books. We're not going to redo the glossary.
No.
Think of this as a conceptual map. We want to give you those aha moments so that when you go back and read, say, Leninger's chapter on water, the diagrams actually make sense.
Precisely. This isn't about memorizing the boiling point of water. It's about understanding the matrix that holds life together. If you understand water, you understand why DNA twists.
You understand why proteins fold.
You understand why your cells don't just explode.
So, let's unpack this. If water is the invisible architecture, we have to start with the brick itself, the molecule. H2O seems so simple. 2 hydrogens, 1 oxygen, done.
It looks simple, right? But Leninger opens with a reality check. If water were actually simple, if it followed the standard rules of physics for a molecule of its size, it would be a gas at room temperature.
A gas.
A gas. We wouldn't be here. Life wouldn't exist. So the magic has to start with the geometry of the molecule itself.
Okay, let's visualize this. I always picture a sort of Mickey Mouse head. Big oxygen face, 2 little hydrogen ears.
That's a decent starting point, but it misses the 3D reality. Leninger describes the water molecule as an irregular tetrahedron.
A tetrahedron. Okay, that's a pyramid with a triangular base. But wait, I'm visualizing the molecule. 1 oxygen, 2 hydrogens. That's 3 points.
Right.
A tetrahedron needs 4 corners. Where are the other 2 corners coming from?
And this is where people get tripped up, and it's the key to absolutely everything. You have to look at the invisible parts of the oxygen atom. Oxygen has 8 electrons. It uses 2 to bond with the hydrogens.
Okay.
But it has 4 left over 2 pairs of them.
The lone pairs.
The lone pairs. And these aren't just abstract concepts. These lone pairs are physically taking up space. They are distinct, dense clouds of negative charge sticking out from the oxygen.
So you've got the oxygen nucleus in the center.
At the center, at 2 corners of the pyramid, you have the hydrogens, and at the other 2 corners, you have these big, bulky clouds of electrons.
So that creates the 4-cornered shape.
Yes. But, and here's the detail that Leninger really stresses, it's an irregular tetrahedron.
Irregular how? What does that mean?
Well, in a perfect geometric tetrahedron like methane, for example, the angle between any of the corners is 109.5 degrees. It's perfectly symmetrical.
Right.
But in water, those lone pair electrons we just talked about, they're really crowded. They're repulsive. They push against each other, and they push against the hydrogen bonds.
So they're kind of bullying the hydrogens.
That is the perfect word for it. They are bully electrons. They squeeze the hydrogens closer together. They literally compress that bond angle from 109.5 down to 104.5 degrees.
That seems like such a tiny difference. And does 5 degrees really matter that much?
It matters for everything. That specific angle, combined with oxygen's electronegativity, its incredible hunger for electrons, creates this massive electrical imbalance. The oxygen side becomes partially negative because of those lone pairs.
And the hydrogen side is partially positive because the oxygen is basically stealing their electron density.
Exactly. So the molecule is a magnet.
A permanent dipole, it has a positive side and a negative side.
Yes. And because of that specific 104.5-degree angle,
Mm-hmm.
water molecules can stack together in a very, very specific way. The positive hydrogen of one molecule grabs onto the negative oxygen of another.
And that's the hydrogen bond.
That is a hydrogen bond. And Leninger points out that individually these are weak. It only takes about 23 kilojoules per mole to break one. Now compare that to 470 kilojoules for a covalent OH bond.
So they're flimsy, like really flimsy.
Individually, yes. They're about 10% covalent and 90% electrostatic attraction.
Yeah.
But collectively, they are a force of nature. And this is where Leninger's flickering cluster metaphor comes in.
I saw that term in the text, flickering cluster. It sounds almost poetic.
It describes the speed. In liquid water, a hydrogen bond lasts anywhere from 1 to 20 picoseconds.
Per seconds.
Trillions of a second. They break, they reform, they break, they reform constantly.
So water is cohesive, it sticks together, which is why water beads up on its tail, but it's also fluid.
It's a dynamic, ever-changing web. The molecules are dancing.
And this dance changes when it freezes, right? Because this is one of the few facts I actually remember from high school physics. Ice floats.
And Leninger explains why that is so profoundly weird. Usually, solids are denser than liquids. But when water freezes, that kinetic energy drops. The molecules stop dancing and they lock into place. And because of that 104.5-degree angle in the geometry of the hydrogen bonds, they lock into a rigid lattice where every single molecule is held at arm's length from its neighbors.
So they are pushed further apart in ice than they are in liquid water.
Exactly. In liquid water, they're all jumbled and averaged out, so you get about 3.4 bonds per molecule. In ice, you get a perfect crystal with 4 bonds per molecule. But the spacing is wider. It creates this open, airy structure. Less dense.
So ice floats.
And thank goodness it does. I mean, think about the biosphere. If ice were denser than water, it would sink to the bottom of the ocean.
The ocean floor would be permanent ice.
Exactly. Lakes would freeze from the bottom up.
Yeah.
In winter, everything in the water would die. The insulating layer of ice at the top is what protects all the life below.
It's just wild to think that the entire history of aquatic life depends on a bond angle being 104.5 degrees and not 109.
It really is the architecture of life.
Yeah.
But let's move from the physics to the chemistry, because Harper talks a lot about water as a solvent. We've all heard like dissolves like.
Right. Polar dissolves polar. Oil and water don't mix. We get it.
But why? This brings us to a concept called the dielectric constant. Harper gets into the math here, but the concept itself is just beautiful.
Okay, break it down for us. What is a dielectric constant?
Think of it as a measure of a solvent's ability to screen charges, to basically hide a positive charge from a negative charge.
Okay.
Water has a very, very high dielectric constant, about 78.5 at room temperature. Now compare that to a nonpolar solvent like benzene or hexane, which is down around 1.9.
Okay, so water is a 78, hexane is a 2. What does that difference actually do in practice?
Imagine you drop table salt sodium chloride into water. In the dry crystal, the positive sodium and the negative chloride are hugging each other very tightly. It's a strong electrostatic attraction.
Right, like a little magnets.
But when they hit the water molecules swarm them. The partially negative oxygens surround the positive sodium. The partially positive hydrogens surround the negative chloride.
They form a little posse around each ion.
They form a hydration shell. And because water has this high dielectric constant, it effectively neutralizes the attraction between the sodium and the chloride. It says to them, you two don't need to hold hands anymore. It screens the charge.
So the force of attraction drops by a factor of 80.
By a factor of 80. So the salt just falls apart. It dissolves.
Right.
Now, imagine this inside a protein. Harper points out that the inside of a protein is often oily hydrophobic. It excludes water. So the dielectric constant inside a protein is very low.
So if you have a positive and a negative charge inside a protein,
they attract each other with incredible force, much, much stronger than they would on the outside surface of the protein. And this is how proteins stabilize their structures, by highlighting these salt bridges deep inside where the water can't get in to weaken them.
That is a crucial distinction. Context matters. A charge on the surface is weak. A charge buried in the center is strong.
Exactly. But water isn't just dissolving things, is it? I mean, it's not just a passive bath. Harper calls it a nucleophile.
A nucleophile, which sounds aggressive.
It is. A nucleophile is an electron-rich species that attacks an electron-poor species. Water actively participates in reactions. The most famous one, of course, is hydrolysis.
Hydrolysis, water breaking.
Right. This is how we digest food. If you eat a steak, you're eating long protein chains. Your body needs to break those chains into individual amino acids. Water acts as the scissor. It attacks the peptide bond and splits it.
But wait, I have a question here. If water is an aggressive scissor that's designed to cut proteins, I am made of proteins, and I am, what, 70% water? Why don't I just dissolve into a puddle of amino acids right now?
That is the great paradox. And the answer lies in the difference between thermodynamics and kinetics. Thermodynamically, the water wants to break you down. It is energetically favorable to hydrolyze your protein.
And it's comforting.
But kinetically, the reaction is incredibly slow. The energy barrier to start the cut is very, very high. So without help, the water just bounces off. We are metastable. We are stable only because the reaction would take, 100 years to happen on its own.
But when we eat that steak,
We add an enzyme. The enzyme's job is to lower that barrier. And then, snap, the water attacks and the bond breaks in milliseconds.
so life exists in that gap between what the water wants to do and how fast it can actually do it.
Perfectly put. Now, we've talked about water dissolving salt, but we have to talk about the opposite. The stuff water hates, the oil, the fat. And this brings us to the hydrophobic effect.
This is a huge topic in Leninger.
In my opinion, it is the single most important concept for understanding how life is organized. And I want to pause here because Leninger drops a truth bomb that completely changed how I see biology.
Okay, lay it on me.
We're all taught that oil and water don't mix because they repel each other. Like magnets with the same polarity pushing apart.
Right. Hydrophobic, fear of water.
But strictly speaking, that's a lie. Nonpolar molecules like oil or the lipid tails of your cell membranes don't really repel water. They're actually slightly attracted to it via very weak van der Waals forces.
Wait, if they aren't repelling each other, then why do they separate? Why does my salad dressing separate?
Because water loves itself more. And even more importantly, because the universe demands chaos.
Entropy.
Entropy. Think about it this way. In liquid water, all molecules are dancing. That flickering cluster we talked about. It's a chaotic, high-entropy party. Everyone is moving, swapping partners. It's great.
Hey, I'm at the party.
Now, drop a glob of fat into that party. The fat molecule is nonpolar. It can't hydrogen bond. It's just a wall. The water molecules right next to that fat glob have a problem. They can't dance with the fat. And they can't easily dance with the water behind them because the fat is blocking the way.
So what do?
To maintain stability and maximize their own hydrogen bonds, they have to link arms with each other around the fat. They form a rigid, stationary cage. Leninger calls it a clathrate.
A cage. So the water touching the fat is forced to stop dancing.
Exactly. It freezes in place. It becomes highly ordered.
And high order means low entropy.
Which thermodynamics absolutely forbids. Nature hates ordered water. It costs way too much energy to keep things that organized. So how does the system fix this problem?
Well, if the problem is the surface area of the fat that's trapping the water.
You minimize the surface area, you smash all the little fat droplets together into one big blob. By doing that, you dramatically reduce the total surface area that's exposed to the water.
And that releases all the trapped water molecules back into the party.
Bingo. The entropy of the water increases. The system relaxes into a more chaotic, favorable state. So, your cell membranes, the very barrier that defines you, isn't held together by the lipids holding hands.
It's held together by the water violently crushing the lipids together so that the water itself can stay messy.
That's it. It is the organizing force of life. The invisible architecture pushes all the non-polar stuffs together. This is what drives protein folding too. Why do proteins curl up into these complex balls?
To hide their hydrophobic amino acids in the center, away from the water.
Yes, so the water doesn't have to form those ordered cages around them.
It's amazing. We focus so much on the stuff, the protein, the fat, but it's the water that's pushing them into place.
And once they are in place, they have to stay there. This brings us to what you could call the Velcro of biochemistry, the weak interactions.
Right. Leninger and Harper both list 4 main types. We've touched on hydrogen bonds and the hydrophobic effect.
Then we have ionic interactions. So the attraction between positive and negative charges and van der Waals forces.
Van der Waals, that's the gecko force, right?
Indeed, these are very, very weak attractions between all atoms, regardless of charge, but they only work when atoms are super close, basically touching distance.
So why do we care about all these weak forces? Why doesn't biology just use strong covalent bonds for everything? Wouldn't that be more stable?
It would be too stable. This is the Goldilocks principle of biochemistry. Covalent bonds are like superglue. If an enzyme bound to a substrate with a covalent bond, it would never let go. The reaction would happen once, and then the enzyme would be clogged forever. It would be useless.
I see. So you need sticky but not stuck.
Exactly. Weak interactions are reversible. They're like Velcro. You can stick a hormone to a receptor, trigger a signal, and then you can peel it off. You can unzip DNA to copy it and then zip it right back up. Life is dynamic. It needs to move. Weak interactions allow for that movement.
And it's strength in numbers, right? One little strip of Velcro is weak. But if you have 1,000 little hooks, 1,000 van der Waals, and hydrogen bonds, you can hold a huge protein structure together very, very tightly.
Correct. The native functional structure of any macromolecule is simply the shape that maximizes all of these weak interactions simultaneously.
Okay, let's pivot a little. We've talked about water structure and its solvent properties, but Harper gets very serious about another aspect of water, its ionization, pH.
This is where we move from structural biology to high-speed electronics almost.
We tend to think of H2O as being this super stable thing, but it does split apart, right?
It does, very, very slightly. It splits into a proton, plus less, and a hydroxide ion. In pure water, the concentration of protons is tiny. It's $1 times 10^7 a molar.
Which gives us our neutral pH of 7.
Right. But here's a mechanism that blows people's minds when they first hear it. These protons, they don't swim.
They don't swim? What do you mean?
Not like a sodium ion swims through water. A proton is just a nucleus. It's absolutely tiny. In water, it immediately attaches to a water molecule to form hydronium, 3 plus $. But it doesn't stay there. Leninger describes this as proton hopping.
Is this the Grothus mechanism?
Yes. Imagine a bucket brigade of firefighters. The water molecules are the firefighters standing in a line. A proton is passed to the first water molecule. That molecule instantly becomes unstable and passes a different proton to the next one, and so on down the chain.
So the original proton itself isn't traveling the distance. It's the charge that's traveling.
Exactly. It's like a wave moving through a stadium crowd. The people don't run across the stadium, but the wave does. And this makes acid-base reactions in water exceptionally, almost unbelievably fast. Way faster than diffusion.
And biology actually uses this.
Everywhere. Leninger gives the example of cytochrome F in photosynthesis. It uses a literal wire of 5 bound water molecules to hop protons across a membrane. It's a wire made of water.
That is incredible. So water is conducting electricity, in a sense, or at least conducting protons.
Conducting information and energy. Now, when we talk about the concentration of these protons, which is pH, we have to talk about the math, because it traps students all the time.
The logarithmic trap.
Right. The pH scale is a log scale. So a shift from pH 7 to pH 6 doesn't mean a little bit more acid. It means 10 times more acid. A shift of 2 pH units is 100 times more acid.
And Harper really drives this home with blood pH. The normal range is what, 7.35 to 7.45? That is a tiny window.
It is razor thin. If your blood pH drops to 7.2, you are in severe acidosis. If it drops to 7.0, which is chemically neutral, you are essentially dead.
Wait, 7.0 is the pH of pure neutral water. Why does neutral water kill me?
Because your enzymes are exquisitely tuned. They've evolved to work at exactly pH 7.4. At 7.0, the protonation states of all your proteins change. The Velcros stop sticking, the charges flip, the shape unravels. Your entire metabolism just crashes.
So how do we stay in that tiny window? If I drink a soda, which is acidic, or I exercise and make lactic acid, why don't I just die?
Buffers.
The unsung heroes.
A buffer is basically a chemical sponge. It soaks up extra protons if the environment gets too acidic, and it can release them if it gets too basic. Its whole job is to resist change.
And this brings us to the dreaded Henderson-Hasselbalch equation.
The bane of many medical students, but it's actually a very simple concept. It just describes the relationship between the pH, the pK of the acid, and the ratio of the acid to its conjugate base.
Let's decode it a bit. What does it actually tell us in a practical sense?
It tells us that a buffer works best when the pH is close to the buffer's pK. That's the flat part you see on a titration curve. In that region, you can add a lot of acid or base, and the pH barely moves.
And Harper lists the big ones for our body, phosphate and bicarbonate.
Phosphate is a great buffer for the inside of our cells. But bicarbonate, that is the absolute MVP of the blood. And that's because it's an open system. It uses 2O2O22.
Carbon dioxide, the stuff we breathe out.
Right. CO2 dissolves in our blood to become carbonic acid. And this links your breathing directly to your blood chemistry. This is the crucial physiological link. If your blood gets too acidic,
the body needs to get rid of acid.
So what does it do?
It breathes it out.
It triggers your lungs, you hyperventilate, you start breathing faster and deeper.
But blow off more 2O22.
Exactly. Less 2O22 in the blood means less carbonic acid. Less acid means the pH goes back up towards normal. You were literally regulating your body's chemistry with your lungs second by second.
That is a perfect segue into the clinical side, because Harper moves us from the physics of entropy to the life and death reality of pH. And you found a story in Leninger that I honestly thought was an urban legend until I saw the citation.
The Legend of JBS Haldane. This is from Box 2-1 in Leninger. It's a masterclass in do not try this at home.
This was in the 1920s, right? The Wild West of physiology.
Oh yeah, the 1920s. Haldane and his colleague Davies wanted to understand acidosis. They wanted to know exactly how the body compensates when blood pH drops. But they didn't have a convenient pool of patients with, say, diabetic ketoacidosis just waiting to be studied.
But volunteered themselves.
They became their own rabbits, as they put it. Haldane decided he needed to acidify his own blood. His first plan was to drink dilute hydrochloric acid.
Battery acid.
Basically. But he did the math, the stoichiometry, and he realized to get the effect he needed, he'd have to drink something like 1.5 gallons of this stuff.
Which is a bit of a volume problem, aside from the whole melting your esophagus problem.
Exactly. He tried a pint, burned his teeth, burned his throat, and decided that was a bad idea. So he switched strategies. He started eating ammonium chloride.
Which sounds like a floor cleaner.
It's a salt. But when it gets to your liver, it gets metabolized into urea and hydrochloric acid. It's essentially a time-release acid bomb.
So what happened to him?
He describes the progression with this terrifying scientific detachment. First, he gets breathless. He's just sitting in a chair, but he starts panting like he's just run a marathon.
That's the buffer system we just talked about kicking in, the bicarbonate.
It is. Blood is turning acidic.
Yeah.
The bicarbonate is grabbing the protons, turning into CO2, and his brain is screaming, breathe, to blow off that CO2. He is literally exhaling the acid.
But I'm guessing it wasn't enough.
Not even close. The headache sets in, then the nausea, then the mental confusion. He effectively induced the symptoms of a diabetic coma in a perfectly healthy man. And the data they got from that, the blood gas values, the urine pH changes, laid the foundation for how we treat acidosis in the ER today.
It's incredible. And then, because they were thorough,
they did the opposite. They ate massive amounts of baking sodium bicarbonate to induce alkalosis. And the result was the inverse. They basically stopped breathing. Their bodies refused to breathe. Because if you don't breathe, CO2 builds up in the blood. CO2 is acidic. The body was desperately trying to acidify the blood to fight the baking soda. They were turning blue, fighting the urge to pass out, just to prove the mechanism of the buffer system.
Wow. It just highlights how physical these mechanisms are. It's not magic, it's titration. You are a walking test tube.
You really are. And speaking of test tubes and balance, we have to talk about osmosis, because Leninger and Harper both stress this, and it's the other side of the water coin.
Osmosis. Right. The movement of water from high water concentration to low water concentration. Or, more intuitively, water moves to where the salt is.
Water follows salt. That's the medical mantra.
So if you put a cell in pure water, a hypertonic solution, water rushes in. The cell swells and bursts. Lysis.
Which is exactly why we don't give patients IVs of pure water. Never, ever. You give saline, isotonic saline. You have to match the osmolarity of the blood. If you gave pure water, you would literally explode the patient's red blood cells.
And Harper mentions a specific disease here that really clarifies how active this process is, nephrogenic diabetes insipidus.
Yes, this is a profound failure of water balance. Normally, your kidneys have these little water channels, aquaporins, that reclaim water from your urine so you don't dehydrate. A hormone called ADH tells them to open up and let water back in.
The don't pee hormone.
Basically. In this disease, the genetic machinery is broken. The kidneys ignore the ADH signal. They don't reclaim the water.
So the water just leaves the body.
Massive amounts. The patient pees out huge volumes of very dilute urine. They are constantly thirsty, constantly drinking because their water logic is fundamentally broken. It really shows that water isn't just something we drink. It's something our body has to actively manage every single second.
So we've covered the molecule with its bully oxygen, the solvent power, the entropy-driven hydrophobic effect, the proton hopping wire, the buffers, and the clinical disasters.
We have been on quite a journey through a simple glass of water.
If we had to summarize the mission of this deep dive, what's the one thing you want the listener to walk away with?
It's that water is the matrix. It's not just the solvent, it's the organizer. It forces lipids to build membranes. It guides proteins to fold correctly. It serves as the wire for protons. It screens charges so chemistry can happen at all. You cannot understand the biology if you ignore the water.
It's the invisible hand, the invisible architect.
It is. And here's a final provocative thought for you, something to chew on.
Hit me.
We talk about water as the solvent, moving around freely. But if you look at a high-resolution crystal structure of a protein like hemoglobin, you often see individual water molecules trapped inside the crystal,
Trapped.
bound, fixed in space. They are hydrogen bonded so tightly to the protein that they don't move. They show up in the X-ray diffraction pattern, just like the carbon and nitrogen atoms of the protein itself.
So they are effectively part of the protein.
Exactly. They are structural. Without those specific, perfectly placed water molecules, the protein would collapse. So the question becomes, where does the water end and the life begin?
Whoa.
The distinction is a lot blurrier than we think. We aren't just bags of water. We are water-organized structures, where the water is sometimes the scaffolding itself.
That is going to keep me up at night. Where does the water end and the life begin?
It's a good question to think about.
Listeners, if you want to see the flickering cluster or the titration curves we talked about, go open Leninger and Harper. The diagrams of the water lattice and those clathrate cages are worth the price of admission alone.
Absolutely. Visualizing that entropy effect really makes it click.
Thanks for diving deep with us. We'll see you next time.
Stay hydrated.